initially planned to be physical. Last year, when we were chalking it out, we thought of inviting distinguished scholars to Pakistan and different OIC member states. But at least for the time being, we are connected online. Comstech has been introduced. Comstech is one of 3 standing committees comprised of 57 ministers of science and technology in OIC countries. This is the second largest group of countries after United Nations. And our responsibility in Comstech, headquartered in Pakistan and chaired by the President of Pakistan, is to work towards the implementation of Science and Technology Agenda 2026, which is a collective commitment of OIC member states, and to develop cooperation between the OIC member states in various aspects of it. And I think the most important aspect is capacity building and developing institutional linkages. This lecture series is certainly an extremely important one. We have been waiting for this presentation since long. There are a lot of people already registered, so I'll tell you that there were going to be about 200 people coming online. So it's already from, I don't know, Hasima, but I'm sure that's about 30 countries or more. And so it is a very popular lecture, has attracted lots of attention. And for that, we have requested very dear friends of ours, Professor Dr. Samar Hasnain, to introduce someone of the stature of Professor Dr. Gautam Desiraju, because that is very befitting to invite someone who know Dr. Desiraju since long and who has worked with him on lots of global projects. With this, I would request Professor Dr. Samar Hasnain for introducing the speaker of today.
Thank you very much, Professor Iqbal. It's a real privilege to introduce Professor Gautam Desiraju, who I got to know nearly 10 years ago. So a decade has gone, and it seems like yesterday. Gautam still looks as fresh as when I met him the first time in Boston. And it's been a privilege to know him. He's an enlightened person. There are not many enlightened fellows around these days. Let me try to give a brief introduction, but most of you know already probably as much as I know, but I will just give you personal reflections. Gautam did his studies in Bombay, which is known as now Mumbai, and then went off to America to do his PhD and where he obtained his PhD in 1976 at the University of Illinois at Urbana-Champaign, where he worked with under the supervision of pioneers of the field, David Curtin and Ian Paul, who were very much interested in organic materials. He was lucky enough to, I should say, Gautam, having seen Hyderabad, to come and join Hyderabad, the University of Hyderabad in 1979, which is a wonderful city of huge historical importance. And it's no wonder that he stayed there for 30 years. Even though he has moved to Bangalore, he still remains fondly in love with Hyderabad, and it's no surprise. He became a reader, then he became a professor at the University of Hyderabad, and eventually became the dean of the university for 3 years. And I think he decided very wisely that he was probably traveling the road where he didn't want to be, and really wanted to remain a research scientist of highest caliber. So he moved on to one of the best institutes of India, the Indian Institute of Technology in Bangalore, which is really world famous Indian Institute of Science, where many of us know many people of huge distinction. And I think Gautam move there benefited IISc hugely, putting that much more on the map of an important field which Gautam had pioneered when he was at the University of Hyderabad. And that is what we are going to be hearing about, known as crystal engineering. It probably is not an exaggeration, and I think Gautam lighting of the camera is not sufficient that we can see Gautam blush. That not only that he pioneered the field, one is legitimate to say that he created the field of crystal engineering, which has become very famous. He's received numerous awards. I'm not going to talk about it, too many to list. But just to say that he became nearly 20 years ago, in 2002, a fellow of the the World Academy of Sciences, which both Iqbal and I cherish and share. And then he became fellow of the Royal Society of Chemistry, fellow of the American Association for Advancement of Sciences, and then at the pinnacle of what I would describe, of our field, he became the president of the International Union of Crystallography, which was founded by Sir Lawrence Bragg, who was one of the creator of the other important field of science, which both I and Gautam share, known as crystallography. And he created that just a year after Pakistan and India were born, that is in 1948. He's a member of several editorial board, advisory boards of many journals. The one I'm going to only highlight, leaving chemists out, that is JACS and Angaventa, all those standard journals. He became the founding inaugural main editor of the chemistry and the crystal engineering section of the journal, which carries the IUCR's name, known as IUCRJ. So this is during the creation of IUCRJ, I worked very closely with Gautam, got to know him very closely, and in his vision for the future. So I guess I've already said that he has not only helped to establish the field of crystal engineering, his vision is that this is an important field at the intersection of chemistry, material science, and crystallography. He has worked tirelessly to expand the field and encourage young people to take up this important field and make contributions to novel materials. I think I think this is probably the right time to say, Gautam, we're very much looking forward to hearing you about the crystal engineering and the current trends and your future vision of how this field is going to develop. So we're looking forward to Gautam in the next 40 minutes or so. Thanks very much, Gautam.
Well, why don't I start by thanking you, Iqbal, for this very kind invitation to speak in the Comstech forum. And it's something that I do look forward to. And thank you to you, Samar, for these very kind personal words, almost, introducing me. And it is true, crystallography has brought the two of us together. And Samar, as the editor-in-chief of all the IUCR journals, 9 of them, for a critical period of 6 years, I think has really made a huge, huge difference in the present standing and status of these journals. He said that I was a bit, say, behind the starting of this new journal, IUCRJ, which was an open access journal, a new idea for IUCR at that time. But let me also say that it was Summer who coined the name. And he pointed out that IUCR being in the publication business, there wasn't a single journal with the IUCR name in it. I mean, if you have JACS, it is Journal of the American Chemical Society. Their most important journal has the name of the society in it. So Summer coined the name IUCRJ, and the name has stuck and it is doing very well today. So I am pleased, and in the course of an hour, I hope to say something about crystal engineering. Before that, let me share the screen, please. So I suppose everybody can hear me properly.
Yes,
Summer,
sir.
are you able to hear?
Yes.
Able to hear properly?
Yes, we are.
Yes, we can.
No distortion or echoes.
Yes,
No
it's
echo.
Okay, let me share the screen. And well, here we go. And I would like to talk to you about crystal engineering. I feel that Summer very kindly says that I created. No, I didn't really create it. The name was there. The name was there since 1955. But I suppose I gave it a new look in 1989. So we'll leave it at that. Now, before that, and before we get into chemistry proper, comstech is an organization which is the science wing of the Organization of Islamic Countries. And I am keenly aware of the fact that not too many people from India might have spoken under your auspices before. And I would like to recollect the memory of Acharya Prafulla Chandra Ray, whom many consider the father of chemistry in India. We call him Acharya, which means somebody who teaches you a skill. Now, all Indic languages have different words for teacher. And I am given to understand that the corresponding word in Urdu is hazik. I am not very sure whether this means somebody who is merely skillful or somebody who imparts skills to others. Probably the meaning is both. And normally when we talk about Acharya in a chemistry context in India, we are always talking about P.C. Ray. He was, I think, the second PhD from India, and that too from the University of Edinburgh in 1888. And he was in turn a chemist, a visionary, a philanthropist, and even a historian, because his 1906 book, A History of Hindu Chemistry, is still read, and it has seen a renaissance because he meticulously quoted and codified contributions of India to the chemical sciences starting from the time of the Vedas. And it is remarkable that the people from this part of the world were able to carry out the advances that they did. As a typical example, we have recognized that zinc was a metal almost 4 to 5 centuries before anyone in Europe was able to recognize that. But this is not a lecture on Ray. What I want to talk about is the convocation address he gave in the Aligarh Muslim University in 1923. And this was, Samar spoke about partition. And Aligarh AMU in specific was a center where there was a lot of discussion going on about Hindus and Muslims in India. This is what Ray said. It is so important for this particular audience that I will read it out. I confess and I trust my friends here will not take it amiss that I am not much in love with sectarian and denominational institutions. And I always tremble with fear lest they degenerate into narrow and bigoted things, as is their general tendency. What wise words. So this invitation to a non-Muslim gave me all the more pleasure on this account that it showed unmistakably the liberal and Catholic spirit that is working in the organizers of this university. I can say the whole thing here, Iqbal, and just replace comstech with this university. And this is how I feel today. And I quoted this same thing when I went to Aligarh myself in 2019, where the university gave me a Lifetime Achievement Award. And it was a memorable occasion. As you can see, the students wouldn't let me go, actually. I had to take a car and go back to Delhi, and I was getting delayed because they simply wouldn't let me go. And so you can see this is the same spirit with which Acharya went to Aligarh in 1923 that I went to Aligarh 100 years later. And I was taken around and I was shown Syed Ahmad Khan's house. And he talks to both Hindus and Muslims. He says, do you belong to a country? This is 1884, by the way. Do you belong to a country other than India? Are you not buried in the same soil, or are you not cremated on the river banks of this land? You die on this land and live on this land. Therefore, remember that Hindu and Muslim are words denoting religious terms. Otherwise, Hindus, Muslims, and Christians too live in the same country and are thus, in this sense, a single nation. It is very much in the spirit of Sir Syed Ahmad that I will be, speaking to you today. And with this, I want to get into the subject. Now, what is crystal engineering? It is the design of molecular solids, their internal structures and external morphologies. There are three aspects in crystal engineering. The understanding of interactions. So understanding interactions. In the context of crystal packing, utilization in the design of new solids with some properties. So there is interactions, design, properties. These are the three key words here. Interactions lead to design, lead to properties. This theme, which I stated in this book, in 1989 has stood the test of time. And crystal engineering has now become very, very diverse, and it is of the greatest relevance to the chemical and structural sciences. This is the aspect which, I wish to talk about more closely today. Now, the core issue. The organic chemists make molecules, but they don't know how they crystallize or in what manner and fashion they crystallize, because the crystal structures cannot be predicted easily from molecular structures. The behavior of a functional group in a molecule depends on the nature and positioning of all the other functional groups. So in other words, each group affects all the others. So it's a kind of a multivariate problem. Crystal structures are not related to molecular structures in simple ways. They are emergent properties. Now, one of the strangest examples of this we found in our own work was this bromocubane carboxylic acid. Acids, as you know, exist in two conformations, the syn and the anti. Usually, well, always, it is either the syn that is found in the crystal or the anti that is found in the crystal. Now, here is a weird structure where you have both syn and anti in the same crystal structure. The reason for this is not hard to find. You see this auxiliary interaction. This is the OH-O hydrogen bond. These things here, which is very common in acids. But now you find this less common. Well, it was less common 20 years ago. The CH-O hydrogen bond. And chemists will recognize quickly that this cubane CH group is very acidic compared to other aliphatic CH groups. So this CH is quite activated and forms a nice hydrogen bond with this carbonyl oxygen. And it is this auxiliary interaction that forces the main interactions to change their whole disposition. Weak controls strong. This is a theme Summer will recognize, which is repeatedly seen in biological structures. A combination of weak interactions is often better or can dominate even sometimes one or two strong interactions. But however beautiful this structure may be, this still leads to the problem of prediction. So some simplification is needed in the way in which we are able to understand crystal structures. You can't take each molecule a priori and then try to determine what the crystal structure is going to be. Some simplification is needed, which helps us to understand molecular recognition. And this I provided in my rather well-known article in Angewandte in 1995 on the supramolecular synthon. So these things are actually structural units in molecules which are preferred modes of association. So the molecule may have so many functional groups and so on. But if certain combinations are present, they tend to dominate in the crystal structure. And so by recognizing these synthons or patterns in crystals that occur more often than others, one is really able to simplify the problem. You identify certain key groups and therefore certain key synthons. And since crystallization is kinetic, it is these key synthons and key interactions which determine the outcome of the crystallization, that is the final crystal structure. So this synthon model brought a lot of simplicity into a very complicated problem. It also does not involve any computation or calculations. So as a result, chemists took to it very readily and started using this synthon model to design new crystal structures. Remember, I told you crystal engineering starts from interactions and then goes to design. So this was the crucial step that takes you from interaction to design. There are all sorts of interactions. We can just enumerate them here, and these are very well known: hydrogen bond, van der Waals, and more recently this halogen bond. This thing is now becoming very, very popular, And it is also being used in crystal engineering. And we ourselves have done some work on this. And they are a bit like hydrogen bonds because the halogen is electrophilic in these cases. But they are different still. So this is a very hot and active topic in crystal engineering today. Now, I don't want to give you too many examples of crystal engineering from our lab. And that would be a whole lecture or many lectures in itself, because today's talk is more about the outlook and prospects of the subject. So this is mostly in the way of a preliminary introduction. But multi-component crystals, or crystals as they are called, is an extremely important aspect of crystal engineering today. Now, usually when you crystallize, the whole idea of crystallization is to purify. It is to take out a pure compound from a mixture. Ever since humankind obtained salt and sugar from brine and molasses, the idea behind crystallization is to use it as a means of purification. Now here you're doing the opposite. You're actually putting two things together and asking them to go into one crystal. This seems almost counterintuitive. Now, binary co-crystals have been known for a long time, since 1840 actually. You can put two things together. Putting three different things together in stoichiometric amounts, not solid solutions, stoichiometric amounts, is more difficult, and it is only about 20 years old. We ourselves got into it about 10 years ago. And the jump from 3 to 4 is extremely difficult. 4 different organic molecules, all of which are solid at room temperature, go into the same crystal in stoichiometric amounts. This is amazing. And the first to do it in my lab were these two gentlemen, Niyaz Mir and Ritesh Dubey, both of whom I suppose are in the audience today. And you see, nowadays, the thoughts of many Indians are naturally running to gold because, you know, we got our first gold medal in the Olympics for an individual event in the athletics part of the championships. So these two guys, Niyaz and Ritesh, they have golden fingers because they were able to get crystals where nobody else can. And in fact, we have now about 30 to 40 of these quaternaries in our lab. And not many people have been, see, I'm sure people are trying to put 4 molecules in a crystal, but we don't see too many reports on stoichiometric quaternaries. It's an example of, you know, an extremely difficult target molecule synthesis. At this level of difficulty, it almost becomes science and art together. There are no, you know, one goes a whole lot by intuition at some stages, as both Niyaz and Ritesh will probably tell you. And this, you know, I give it as a single example of crystal engineering. This is to also tell people in the audience, you know, nowadays, we had a paper recently in Angevante on a ternary co-crystal with only halogen bonding, no hydrogen bonds. And the referee wrote, he said that one of the referees, he says that he or she says, it's a very difficult thing because the authors are trying to do something with one hand tied behind their back. And that is no hydrogen bonding. So why make it so difficult? He says, the only reason is if something is very difficult, you like to try it. This is the way in science. And he also says, she also says, this work is probably of no practical application, but it doesn't matter. This is something I want you to understand. Every piece of scientific work done in the lab does not have to be necessarily of practical application. Some of these things are done simply because they advance knowledge. And through such advances in knowledge, you are able to get new methodologies that will help you tomorrow to make a discovery that is of practical application. So there is no need to have a one-to-one correspondence between what you're doing today and some product in industry tomorrow. But be that as it may, this is, well, how they actually did it. It's easy to explain, but very hard to do. You start off with a crystal, a binary crystal, where one of the molecules is in two different crystallographic locations. And therefore, they become chemically not equivalent. And therefore, they can be touched. So one of these is replaced by this blue thing. And now you have two blue things that are again in different environments. And incidentally, you picked up a third yellow here. And this is the art part. I said it's art and science. No? So picked up the third thing. And these two being non-equivalent, you can then replace one of them only with the green. So we have green, blue, red, and yellow quaternary stoichiometric. And this is typical of the compounds that Niaz and Ritesh made. So I mean, it's very easy for me to explain it and probably easy to understand, but it's extremely difficult to do. So let's now go to the main theme of the talk. And I see that I have about maybe 30-35 minutes. Now, crystal engineering, any subject that has grown so well and so fast, does have those applications. It's not like what I said that you can do all the work you do without a thought to the practical application. The practical application follows if the work is good. So there are 5 topics which I want to cover very, very, very briefly, each of them. The first is in the area of pharmaceuticals, crystals especially. The second is to deal with solid state reactions. The third actually has to do with mechanical properties of materials, organic crystals. The fourth has to do with framework solids that are porous, typically MOFs and COFs. Finally, property engineering, solar energy harvesting, etc. As you can see, you're going from design to properties. All these 5 have nice, interesting, and important properties. And that is why I consider them to be the future. Let's go to pharmaceuticals. Now, the subject has grown remarkably quickly, the subject of pharmaceutical co-crystals. As I said, it began in 95 with my angewandte article on synthons. By 2004, we have Mike Zaborodko talking about heterosyntons. So he divides my synthons into homosyntons and heterosyntons and shows that heterosyntons are the ones that are responsible for the formation of binary co-crystals. And this then quickly led to pharmaceutical co-crystals. That is, co-crystals where at least one of the 2 components is an active pharmaceutical ingredient or API, commonly known as drug. So we go from synthon to heterosynthon to pharmaceutical co-crystal. Then we go to formulation, which is a very important step in the process. And finally, we go to a marketed drug. And today there are 5 of these things on the market. That is, they have completed the whole cycle up to and including FDA approval, manufacture, sale, etc. So synthon, heterosynthon, pharmaceutical co-crystal, formulation, market. All this in 25 years is extremely quick progress in the slow-moving pharmaceutical industry. Now, a great deal was achieved in 2018 when the FDA, the US FDA, reclassified co-crystals. They say pharmaceutical co-crystals have opened up opportunities for engineering. See that word, engineering, solid state forms beyond conventional solid state forms of an API, such as salts and polymorphs. Salts and polymorphs have been around in the pharmaceutical industry salts for a very long time, polymorphs for at least since 1990. So co-crystals has entered this domain of pharmaceutical solid forms. And this 2018 reclassification is very important because it overturned a very retrograde guideline in 2011 that defined co-crystals as solids that are crystalline materials composed of 2 or more molecules in the same crystal lattice. So from this to this was a big jump, and then the floodgates are now open. Every generic pharma company is trying to make the maximum number of co-crystals that it can, because you see, this is a way of extending the useful life of a patent. It is in the innovator's interest to make new co-crystals because the innovator can extend the life of the patent. It is in the interest of a generic to get a co-crystal because then he can claim a new patent under new composition of matter. So both sides of this tussle want to make co-crystals. Now, very quickly, a drug needs to have both high solubility and high permeability. It is ingested like a tablet. This is obvious. It needs to be soluble first to be able to absorb, and then it needs a high permeability so that it crosses the membrane in the gastrointestinal tract. And so membrane permeability is very important. Now, unfortunately, many of the drugs that are being designed today, for reasons that I can't get into, belong to class 2 and class 4. That is, they have either low solubility and high permeability, that is no good in one way, or they have low solubility and low permeability also. That is good in neither way. This is a more common situation. A low solubility drug with high permeability. The drugs are themselves, I would say, hydrophobic in nature. They don't dissolve very well in water. That's the problem. Now, one of our own papers in this area involves a drug-drug salt hydrate of the antibacterial norfloxacin and the antimicrobial sulfathiazole. Now, you see, norfloxacin is extremely insoluble. I mean, look at this. Nothing. But when you make the drug-drug salt hydrate, the solubility of both the components goes up. Sulfathiazole was always soluble. Look at this. This is norfloxacin solubility. This is sulfathiazole solubility, and this is the co-crystal. You see, it goes up. Similarly, for permeability, norfloxacin, sulfathiazole, co-crystal. So, what's going on? You see, once again, synthon theory comes to the rescue. Now, suppose you have a physical mixture of norfloxacin and sulfathiazole, and then you ingest it. Norfloxacin dissolves to the extent that it can, sulfathiazole dissolves slightly more, and norfloxacin is not able to go through the membrane because it doesn't have permeability also. Sulfathiazole has got the permeability, so it will go through. Now, when you have the crystalline salt, we invoke the presence of an extended synthon in solution. This is different from this. Here, norfloxacin and sulfathiazole are quite separate. Here, there is some association through the water. And so this is what we call an extended synthon. And this work is important because it tells us that synthons exist in solution too. It's not just a solid state thing. It is not a motif, which many people wrongly call it. This is a kinetic event. And therefore, synthons are important even in crystallization, in dissolution, etc., etc. So since norfloxacin and sulfathiazole already have a loose association in solution, sulfathiazole is literally able to drag the norfloxacin through the membrane. And so this also tells us a big reason why people should be working with co-crystals, because you can preferentially enhance the properties of an API which is otherwise good, but with low bioavailability. So these are some of the things that are already there in the market. I told you polymorphs, solvates, hydrates, eutectics, but now most important co-crystals, Entresto, 2-glyphosine. These are 2 of the 5 which are in the market right now. And I'm sure there are going to be many more in the near future. The second theme is the theme of organic solid-state reactions. And we come to Gerhard Schmidt, who didn't coin the name crystal engineering, but gave it some shape in the 1950s and 1960s with his pioneering work on the photodimerization of cinnamic acids in the solid state. So just a couple of months before this COVID thing happened, they held a centenary celebration for him at the Weizmann Institute. And, paying one's respects to another Acharya, I would call him. And people say that he gave some form and shape in those early days. I mean, we knew nothing about interactions and so on then. And so it was a nice gathering of people. Professor Lazarowitz and Professor Lahav, 2 of his PhD students from the old days, Professor Eda Yonath, who was a postdoc with him. And then here's me with Professor Mitrangelo, who has done so much good work on halogen bonding. So it was a nice function, and we talked about the old days and also the new days, which are undoubtedly coming now. An immediate way in which this gets into, Schmidt's work gets into, is the modern topic of mechanochemistry. So many of the organic reactions take place quite easily when the mixture of solids is ball milled or crushed or ground or something like that. So here's a nice paper with many, many, VIPs of crystal engineering as co-authors. And this method of grinding 2 solids together, grinding, co-grinding, grinding with the presence of some solvent, which is called solvent-assisted grinding. This is very big even in the co-crystal area, many of which are made in this method. So mechanochemistry is closely connected with organic solid-state chemistry. It's an old subject, solid-state reactions. Many of these classical reactions were shown to proceed in solids. Concerns have been expressed about the truly solid-state nature. Is there a partial melting and so on? Or is there some sublimation, recondensation? But they are certainly used in industry. They have always been used. And as I've written here, they're shrouded in the patent literature. They have a future today with green chemistry and so on. And there will be a lot of progress here. Names like Professor R.P. Rastogi in India, who was the first one to demonstrate co-grinding in the 1960s. Professor Fumio Toda from Japan, who carried out so many standard organic reactions in the solid state. And Professor Vladimir Boldyrev in the Soviet Union, who is still writing fantastic papers at the grand age of 94. I mean, there was a paper from him just 3-4 months back. And so these are all pioneers who have taught us many things. And I think there is something to be said for going back to their old work and trying to re-examine it in the context of modern tools and methodologies. I think there are a lot of research problems here for youngsters to look at simply by looking at the work, again, a relook at the work of Toda, Rastogi, and Boldyrev. There's enough for you to last 30-40 years. Now, the next topic that I come to is the question of mechanical properties of crystals. And in our own way, we started some of this in 2006 when we showed that organic crystals are not always brittle. Many of them can be compliant. They are either plastic, which means that when you deform them, they don't go back to the old shape, or they are elastic. When you deform them, they do go back to the old shape. So on the basis of much of the work that had emerged from my group over the years, we published this article in Accounts in 2018, and which tried to again point towards the way forward. The fact that this is an exploding part of crystal engineering is shown by the fact that there were so many reviews, mind you, these are not papers, since 2018 on this subject. The name of Professor Naumov, Professor Calvin's son, Professor Chandrasekhar, who is in the University of Hyderabad, my old university, Professor Frischi at McGill, Professor Mallareddy, who was my PhD student when the first work on plastic crystals was done in 2006, Professor Bardeen in the US, and last and certainly not the least, my former student Manish Mishra and my former postdoc Saumyajit Ghosh, both of whom are now in independent academic positions in India. All this between 3 years. I mean, just today I was reading a paper. The first paper I read in the morning today was a paper by Chandrasekhar and Naumov on the use of beautiful paper in advanced materials, on how you can use these plastic crystals to make actually integrated circuits. It is research to application all in one paper. 50 years ago when I was a PhD student, my advisor David Curtin whom Samar was kind enough to mention, used to talk about molecular computers, and nobody knew what he was talking about, really. But today when I read Chandrasekhar's paper, I felt that, the age of molecular computers is not far, because the scales at which they can operate are much distant scales, are much lower than silicon. So this is really exciting. 2 weeks ago, Professor Mallareddy had a wonderful paper in Science on the role of mechanical effects in piezoelectric crystals. This is the second paper from an Indian author based in India in Science, in chemistry. So I was talking about gold and so on. So this is another type of gold. To get an individual paper in Science from India is not easy. And yet Professor Mallareddy has done that with his nice work on these piezoelectric crystals. So these are all names you should follow if you are interested in this field. And this is actually Professor Mallareddy's work when he was Mr. Mallareddy, a PhD student. You see these plastic crystals, this is how they look, And it means that there are some deformations in various parts of the crystal. Now, his own work as a professor shows that the crystal structures in all these distorted regions are all slightly different from each other. You have to use synchrotron radiation and examine small bits, and I think this is where electron diffraction will be really important, because you can examine at a micro level what X-ray diffraction cannot do. So this is just for fun. Now, elastic deformation. See, this is a structure, and when the crystal deforms elastically, it is capable of some kind of a linear deformation or an angular deformation like this. And then when you release it, it goes back. So certain types of interactions facilitate elastic deformation. Certain types of interactions facilitate plastic deformation. So the question is, what is what? Now, these came together in a paper that I wrote in 2017 and the student here is Shubhankar Saha, and who has recently taken up a teaching position in India. So here you can actually go from 1D plastic to 1D elastic. Look at it. This is a mounted small needle. magnified, of course. And so when you release the needle, the crystal springs back. And then you can actually have a 2D elastic here. And so that if you turn the crystal on its side and then again deform it again, it becomes elastic. And finally, you can make the crystal into a 2D plastic crystal, which can then actually be twisted. So this is an example of what is called twisting a crystal. Just last week, I was interviewed by the JSES. They're having a new series on something about, chemists whom they consider to be big shots or something. So the editor-in-chief, newly appointed, Eric Carrera, interviewed me, delightful man. And so he was asking me, he asked a very provocative question. He said, if any one of your papers in JAX most closely comes to your personality, which one would it be? So I mentioned this particular paper to him. So Shubhankar, if he's listening to the talk, would like to hear that. So it's full of twists and turns, and it's very convoluted. And because here you have two crystal structures that are the same. This is the bromo compound, this is the iodo compound. The crystal structures are the same, but the property is different. So usually, in crystal engineering and other places, we are used to this idea of structure being correlated with property. Same structure, same property. Different structure, different property. No. In crystal engineering, sometimes you can have same structure, different property. And this is why we call this in that paper 3 generations of crystal engineering. Molecular structure to crystal structure, that is the first. 2 interactions, that is the first step. Interactions to crystal structure, this is done retrosynthetically, and this is the supramolecular synthon. This is the second step. The third step is also done in a retro manner. Crystal structure leads to property, but as I said, not always. So it is simpler and less confusing to go from property to crystal structure. First, you need a property. Identify a property. Then go find a structure that will fulfill that property. Many researchers today, they have a structure. They get fascinated with that structure. They fall in love with their own structure. And so they say this structure can do everything in the world. And they say it can do this, it can do that, it can do. Well, most of the time they get disappointed, because if they had only started with property first, tried to find the structure, they would never be disappointed. So sometimes the manner in which you think, the order in which you think, very, very important in science. So this brings me to the subject of Hofs. These are these famous 3-dimensional porous solids, and they're very old. This is a painting, and this color, this blue color, is called Prussian Blue, and this hangs in an art gallery in Berlin. And Prussian Blue is an example, first example of what can be called a coordination polymer. Basically the kind of stuff that the Hofs are. And the structure of Prussian Blue was only classified recently. They're easy to crystallize, and they form nice crystals, which is why so many crystal structures have been determined. 20,000 have been made. And the very nice article that again I read today in a journal called Communications Chemistry. ComChem it calls itself. It's not chemical communications. It's another journal called Communications in Chemistry by Professor Hong Kai Zhu from China and H.R. Ryder from Oak Ridge in Tennessee, which talks about the fact that Hofs are all great. And he does mention Richard Robson, whom many associate with the beginning of this field. And he talks about Susumu Kitagawa, who was making a number of coordination polymers. And he talks about Omar Yagi, who gave them the name Hofs. And he also talks about Omar Farha, a wonderful, younger researcher from Northwestern, who has now developed a Hof that is able to meet the US standards for uptake of methane, which can be quite important. So But the purpose of this article that Professor Kai and Dr. Ryder have written is not this. It says that porous solids have been known to humankind again almost 3,000 and more years. He talks about Egypt and talks about India. In both these countries, charcoal, all of us know that charcoal absorbs gases and other things and various compounds. When we crystallize something, we boil it with charcoal. Apparently, this was known to the ancient Egyptians and the ancient Hindus. So there are medicinal recipes given to make a concoction with this charcoal and then ingest the same thing. And then it makes you feel better, apparently, because it absorbs all the things. So he says, once again, he says, what I said in solid state reactions. He said, just go back to old chemistry, even ancient chemistry, pre-ancient. Look at some of these systems in a modern way. Now, zeolites, I come to zeolites. He mentions zeolites in this article, and he says that they are very good acidic catalysts, which are used on a mass scale. So the catalytic properties of MOFs, needs to compare with that of zeolites. And this brings me to the biggest problem with these MOFs. Lack of thermal stability, limited chemical stability, water sensitive, many of them. And they have to be zeolites, because this is what is industrially, ruling in petrochemical refining, naphtha cracking, and manufacture. The big ticket applications are missing. A nice article in 2017, she says, for the last 15 years, the elephant in the room has been, where are the applications? So you see, this is what has happened. You've got lots of structures. People are running around saying, my structure is great, and it'll do all these things from A to Z, but we don't have big applications as yet. And these are some of the problems. It is said that they can capture CO2, these MOFs. MOFs will capture CO2, but stoichiometrically. And the molecular weight of the MOF is 10 times that of the CO2. So the amount of MOF needed is quite a lot. And the carbon dioxide that is released in industry has oxides of sulfur, nitrogen, moisture, carbon monoxide, etc., etc. Also under high temperature conditions. The MOFs will survive not these gases, and they won't survive the temperature. They are not temperature stable, they are not water stable, they are not recyclable. And still, the conventional methods of removing carbon dioxide with alkali is cheaper than using MOFs. And with crude oil running at $60 to $70, methane fuel transportation based on MOFs, etc., is a distant dream. Now, in the present era, we probably cannot give up fossil fuels. So we've gone from coal to oil, now to natural gas. And in 10 years' time, we will be more dependent on natural gas as a fuel. And whether or not natural gas is better than oil in terms of overall environment is a question for the green chemistry people to worry about. But what I will say is that we're going to be looking a whole lot more at countries like Qatar, Iran, Turkmenistan, which have got a lot of natural gas. And Qatar, in fact, has developed methods in which this natural gas can be liquefied and therefore transported easily. So I do hope some of these countries are part of comstech, because I think that's the kind of input that the rest of you all will have to get from a country like Turkmenistan, because they really have a lot of natural gas. And so these are the countries to look for in the future. And then another issue, recently I've seen some papers where you can use MOFs to capture moisture in the desert air. And it would seem that in a desert climatic condition, which is present in some of the countries, at least that are in comstech, this looks reasonably attractive on first glance. But then one finds that this is not the real issue. You don't take a structure and then find a property. You see what the problem is first. You see what property you need. Many of the desert places, or even non-desert places like my own country, We have a lot of water, but the water not available all the time to all the people. All this part of India is subject to water shortage, actually, of all these things. You know, all these things are subject to water shortage in the dry season, because we are all fed only with rain-fed rivers. So there is water, but it's not available all the time. So water storage and water transportation becomes so important. And so we have different types of these methods for water storage and water transportation. That is the real problem. You cannot sell a MOF that absorbs water from desert air in one of the third largest economy in the world, because the market simply ain't here. Here am I actually standing. This was again a year before COVID. Everything is now before COVID and after COVID. So this is a year before COVID. I'm standing somewhere in this place. So this is one of these things, and so I mean, they really exist and common people use them all the time. Here is another example, what we call VAV in Gujarat and Rajasthan. The elaborate wells, you see in Rajasthan and Gujarat, all this is actually practically desert. All this is where Hyderabad and other places, all semi-arid, So it's not desert, but almost. So here is the structure of these valves. They are very, very elaborate and very, very deep. And here is one on the 100 rupee note. And this is a very famous one. It's almost a tourist attraction, even though it still works. And so I thought I'll bring some pictures. This is Rani Ki Vav in Ahmedabad. You can see, I mean, it doesn't look like a well actually. It looks like a palace or something like that. But it is a well. Here is another grand example. This photo I took myself. And this is in the famous place Hampi, which used to be called Vijayanagara, which was in 1560 when it was destroyed, the second largest city in the world. The first was Beijing and Vijayanagara was the second. Today it is called Hampi because there is a small place called Hampi nearby there. But this is the step well in Vijayanagara, which still works. Look at this. This elaborate kind of a procedure. All this is semi-arid. Hampi is not very far from Bangalore. It's about 250 kilometers from here. So it's an easy drive to go there. And since Samar mentions Hyderabad, here is the famous well in the Golconda Fort, much more humble in looks compared to Rani Ki Vav and the one in Hampi. But this is also a semi-arid place. Hyderabad is. It gets only a little rain sometime around now. I guess it's raining right now in Hyderabad, but it's not a whole lot. And so you can see in Golconda, this is at an elevation, mind you. It's not even at Golconda is on top of a hill kind of thing. So this is another example. So you see, in traditional countries like ours, we are always going to need and use and depend on water sources of this type. So you find better ways of finding water. You find better ways of transporting the water. That would be a property that you have to identify, and it is for such a property that you would have to find a solution scientifically, not the other way around. So I can keep talking about coughs, but I will not waste time in all these things. And then there's a new one called, what is it called? Hydrogen bonded organic frameworks, Hofs. So these have the advantage that there is no metal atom, but again, a very, I would say, contemplative article by Professor Banerjee, again, one of my former PhD students. It's a perspective article in JAX on these coughs. And he correctly points out that the issues of scalability, stability, processability, especially this last one, are not at all solved in the case of coughs. So, I mean, again, once again, they talk about lots of properties, this and that, everything under the sun. But when the basic problems are not solved, I think one has still a long way to go. But it also means that maybe there is room for some more science here. So finally, I come to the last part, the solar energy functional materials, which is again so very important today. And energy cost definitely is going to fall. By 2030, I spoke about us going from oil to natural gas, but whatever it is, we're not going to need fossil fuel so much. Already you can see the difference in India. Certain parts of South India use quite a lot of electricity from solar energy. And perovskite-based solar cells, conversion efficiencies of 20%. So the question is, what can crystal engineering and organic solids do? They are useful in niche applications. Wearable electronics, sensor devices, medical diagnostics that require flexible solar energy harvesting materials of lower energy output. Like in every other case, the organic substance has a higher tailoring capacity because you can adjust the structures at very micro levels compared to inorganics. So there is a real role for this. So polythiophene, PHT, is a molecule that has been talked about very often in this context. So these PHD molecules can assemble plane to plane, cofacial like this, two parallel things, or plane to edge, like this. So this corresponds to the classical herringbone and sandwich structures that I pointed out with Professor Gavazotti as far back as 88 or 89. So you see, the cycle, it comes back. Things that were said long ago with no apparent, industrial application or any such thing, it comes back after some time, and then people find ways of. So what is that? They're orienting PHD films either in the parallel or the perpendicular orientation, because depending on how you order them, their photophysical properties become entirely different. So you can see, with these 5 themes that I have selected, it tells you that, when you start off with basic scientific ideas, crystals, packing, interactions, how do you put them together so that it just doesn't become an empirical mumbo jumbo? So you have to systematize the design. Now, once you can design something, then after that you can make anything you want. And what do you make? You make it on the basis of the property. So whether it's pharmaceuticals, whether it's a clean, efficient, solid state reaction that can be done on a very large scale, or whether it is tiny crystals that have interesting mechanical properties that can be exploited to get, beautiful control over many kinds of thermal and light-induced properties. Then the porous solids. This to me is the most attractive and the most enigmatic area. And Professor Yagi has recently written again a thoughtful article in Faraday Transactions, where he's saying, so many crystal structures, what do all these structures mean? And people are not looking accurately, closely enough at individual crystal structures. I mean, this is something that we did in the organic area long, long, long ago. People like me, Professor Braga, Professor Bernstein, who sadly has left us last year. We looked at a few structures in great detail, and that gave us enough insights to then expand from the specific to the general. Just doing a lot of structures, and as editor and referee, I see so many papers on these crystal structures of morphs. Yes, they're all good. That's because the diffractometers are good and you can get the crystals are good. Well, what does that structure mean? I mean, this is, I think, something that young authors should face. Anybody can write a paper. And as Professor Hoffman once said, he said, anybody can get any junk published in some place. So publication is not the question. The question is, what impact will it have? What shelf life will that paper have? Will people read it carefully? Will it teach somebody? Will you really be Acharya, at the end of the whole exercise? Or would you just be a person who has written a lot of papers mechanically because that's what you were trained to do? I mean, these are, I think, young people who want to shape their careers for the next 20, 25, 30 years should be thinking along these lines. See, unless you can make some difference with what you do, my sincere advice to you is don't even try to do it. Otherwise, you'll be wasting a lot of time and you'll be wasting a lot of other people's money. This is not a sustainable model today, certainly not post-COVID. So, I end my talk now with this. I mean, this whole journey of crystal engineering, Samar said very kindly that I've created this subject, but in the process of, whatever I did, I have seen and met and interacted with so many wonderful people in, so many places in the world. I mean, this is a meeting that Professor Braga is going to arrange next month. And so I put this up. It's all about walking the walk of polymorphs, co-crystals, and solvates. So clearly this has got to do with pharma. This, I think Iqbal and Samar and some of you will recognize, is me when I came to Karachi in 2014. Talking about Karachi, by the way, I also read recently that Acharya P.C. Ray was given an official welcome by the Corporation of Karachi in 1933. And apparently that was a very big thing in those days for a corporation of a city to welcome an eminent person. Today corporations in India, I mean, would like to keep away from them because for various reasons. But I have heard that about him. So here is me in Karachi. I spoke about Professor Malla Reddy, and here he is. And this was taken at the IUCR conference in Hyderabad in 2017. And this is Francois Dietrich. This is a picture in Geneva. And sadly, he left us last year. For so many years, the editor-in-chief of Angewandte, Professor Roland Boesi, with whom I have had from Germany, with whom I have had many interesting conversations and collaborations over the years. The Gordon Conference meeting in Maine, I think. Professor Nangia, my collaborator from Hyderabad for many years. And here is Professor Naumov, almost like a young boy. Well, I am looking young too here. He's a PhD student in Japan. He's fluent in Japanese. From Macedonia, fluent in Japanese, and works in Abu Dhabi. So, he's a citizen of the world. This was taken in Kyoto, by the way. And this is Professor Zevorotko, of course, the one who gave us the pharmaceutical co-crystals. Professor Omar Yagi and me, taken 2 years ago when we met somewhere. And here is me in Cameroon, talking to the people there about, how to bring the whole message of science into Africa and places like that. So it's been a, wonderful journey all over the place. And this is what tells me that, again, in the middle, what Sir Syed Ahmad said, all of us belong to the same nation of science. Science itself is a nationhood. And I think this is what the real message for scientists. We may be this and that, and we may be eating this and that, or we may be wearing this and that, or we may, be traveling in this and that, but those are all less important compared to these higher domains. And science is certainly in this higher domain. If you see all these pictures in all these places, you get the feeling, and I'm sure many of you can. Samar will probably be able to exchange a set of pictures like this, as would Iqbal, as would some of the others in the audience. So I think this is the real message of crystal engineering, of any other kind of science. Whatever you do with rigor. Do it with rigor and do it with all sincerity. If that stuff is done properly, all the applications, everything else will come. And as the Gita says, you do your work, that is your duty. But to expect the rewards, that is not your duty. So do the work without expecting any return. And if everybody behaves like this, then I think the world will learn a lot from us scientists. I think we are still a cut above the rest of the population. I get that feeling. Within the group of scientists, we are happy to criticize each other. But when you look at us as a group and you look at the general society, outside, you will realize that there is a lot about us group of scientists that is quite different and quite a bit nicer than the general public out there. So I think with these words I will leave you, and once again I would like to thank Comstech, Professor Iqbal Chaudhary, my many students, postdocs and collaborators, the IISc in Bangalore, and I would also thank you all for your very kind attention. Thank you ever so much.
Thank you very much, Professor Gautam. It was such a nice and fascinating lecture to sum it up. Before I take concluding remarks of Professor Iqbal and Professor Samar, if you allow me, can I ask you some questions posted in the chat box for you?
You can, provided I don't know what your time constraints are. I am happy to answer a few questions if you could summarize. You could summarize some of the questions, and if some of the questions look similar to each other.
Okay, sure.
I don't know, Iqbal, is this okay? I mean,
yes, sir. Yeah, everybody is just, you see 160 people totally glued to the screen and fully motivated to listen to you. So I think I will go for questions. Azima.
Okay.
Thank you, sir. So we have one question from Dr. Muhammad Mansoob. Number one, he's saying he have probably met you and listened to your lecture at AMU Aligarh, India. And the question that he has for you is, I would like to know about the inorganic crystal engineering. Could you please shed your views on it?
A very nice question. What was the name again? Mansoor, is it?
Mansoob Khan, Dr. Mansoob Khan.
Dr. Khan is a very good question, because crystal engineering has traditionally been associated with molecular solids. And so then what is inorganic crystal engineering, where you consider typically infinite solids? The answer lies in the definition of a molecule. See, an organic molecule is a zero-dimensional object, and therefore its limits of its molecularity lie in all the three dimensions. Now, if you take a sheet structure, which is common in inorganic structures, it is what can be called a one-dimensional object, because it's got limits on one pair of directions. The molecularity extends in 2 dimensions. If you take a ribbon structure, it is again, you get the idea, 2-dimensional molecule. And if you take a diamond or an infinite structure, a morph, there are no limits on the molecularity. So it is a 3-dimensional molecule. So if you take this kind of a representation, all the inorganic solids come under the definition of molecularity. And when you look at molecular in organic, inorganic hybrids, for instance, you take clathrates, sheet structures, something like, say, molybdenum trioxide. It's got a layer structure in which you can sandwich an organic molecule in the middle. So the inorganic extends in 2 dimensions and the organic comes in the 3rd dimension. So I think once you get away from the preconceived notion that a molecule must be a 0-dimensional object. No, it can also be a 1-dimensional object, layer, a 2-dimensional object, ribbon, or a 3-dimensional object, an infinite solid. Then the methods of crystal engineering can be applied just as readily. Professor Ramanan in IIT Delhi, a postdoc of Stan Whittingham in Binghamton, is working a lot on this idea, and there are many others who are working on this idea. And in fact, I would also invite those in the audience who are interested. Recently, I took up an editorship of the inorganic journal Polyhedron. So you might want to know exactly what a person like me is doing as an editor of Polyhedron, that is supposed to be an inorganic journal. The whole idea is something like this, what Dr. Khan has asked. Can we bring in this whole concept of inorganic crystal engineering? We already have some talk about having a special issue of Polyhedron on inorganic crystal engineering. So I think those who are thinking on these lines are welcome to start browsing Polyhedron and looking at some of the articles. It's very, very conceptually, it's an interesting idea. So we'll have to see where and how it goes. Yes.
Thank you very much, sir. We have another question from Mr. Ghulam Murtaza. He's asking, is it possible to get crystal and co-crystal from solvents like DMSO and DMF? If yes, then how?
Yes. Yes. Interesting is, you call it a co-crystal or not, if one of the components is a liquid at room temperature. So this has been talked about. It could be a semantic issue. So, people say, is a hydrate a co-crystal? Technically, yes. For many practical purposes, no. For patent purposes, maybe not. But you can get a co-crystal with DMSO sometimes by simply crystallizing the stuff in DMSO. And sometimes it's impossible to get good single crystals without a solvent. And in that case, the only thing you get is the co-crystal. So sometimes there are other interesting cases. You can have two gases that come together and which can be crystallized under extreme conditions to form a co-crystal. And the most fascinating example of this, you can look at, I mentioned Professor Boise at the end. He is a world expert at taking gases and liquids and co-crystallizing them together, like say methane and ammonia, something like that. There's a beautiful article recently in Accounts of Chemical Research on the probable existence of co-crystals in the atmosphere of, guess where? It's nowhere on Earth, very far from Earth. It's in a place called Titan, which is one of the moons of Saturn. Because under the conditions that are prevailing in the atmosphere of Saturn, methane and ammonia are actually liquids and even solids. So under the conditions that are prevalent there, because they have found some evidence of crystalline matter out there. And so the question is that, and now there is a group in Australia that is actually written this article. They have good evidence. The paper in IUCRJ, by the way, the first paper in this topic, Summer, was handled by me in IUCRJ about 4 or 5 years ago. Just check up IUCRJ and Titan. You will get this paper. And so they exist out there. So your crystal engineering actually meets, space science. That is how wide this whole thing goes. So definitely, DMSO compared to this, is a very simple example of a co-crystal. Yes, you can call it a co-crystal. Yeah.
Thank you, sir. Last question for today. Dr. Naveed Zafar is asking, what are the demerits of first order phase transition in inorganic?
Say that again. Say that again. Could you repeat the question slightly slowly, please?
What are the demerits of first order phase transition in inorganic crystal engineering? Would it not affect cyclability and stability of crystal due to large volume changes?
Not necessarily, I don't believe. It depends what you want it for. Like if you want to do some sensors and all that, then that would be a disadvantage because you want reversibility in those cases. And so you might be better off with the second order phase transition. But suppose you want to, make another polymorph of something. Then you don't care if it's first order, second order, and there is no inorganic organic distinction in this business. I mean, you have first order and second order phase transitions in both categories of substance. So once again, I would make a plea to chemists, especially today, that this organic inorganic distinction, which is so important in pedagogy, and unfortunately, many of our courses are structured in this organic, inorganic, physical way. It's not easy to fit in some subjects. Certainly, crystal engineering, very difficult to fit in an organic, inorganic, physical categorization. And I'm proud to say that it cannot be. And this is again an example of, I would say, I think Comstech could also look at this. Try to start changing course curricula in some of your member countries and pull it out of the, not even 20th century, pull it out of the 19th century and bring it to the 21st century. Because you need to have expertise in a wide variety of things. Anybody getting into competitive research today needs to be a real expert in one field, but at least have some knowledge of a few other fields. Enough knowledge that you can talk to a collaborator sensibly. You can't have, even in a collaboration, you can't have 2-3 people who simply don't know or don't want to know about the other person's field. So I think it's going to lead also to a new breed of researcher who is much more open-minded and is able to, look at all these aspects. Yes.
Thank you very much, sir. We have a couple of other questions as well, but due to shortage of time, we cannot take them all. With this, I would request Professor Dr. Samar Hasnan to share his thoughts.
Well, Gautam, what a fascinating lecture. That is precisely what we expected. And that is precisely why I said that even though the name crystal engineering might have existed, Gautam is the one who has essentially created it and has brought it to the modern world, bringing the whole facets of chemistry, understanding of the structures, and then relating it to property, starting from again the premise of property, and then defining it in the context of the new structure. As you may have seen, where the structures looked similar, they were obviously some translational elements which make those structures distinct. But you can only do that once you understand the property and the nature of the material and the chemistry behind it. What is very fascinating is to not only listen about the science, but also a plea which is coming from the heart, because he has obviously transcended the scientific traditional boundaries, which is to bring the inorganic chemistry, organic chemistry, which is really nothing but biology, because all biology underneath is chemistry. He talked about the weak interactions being sometimes much more important, despite being even in the presence of stronger interactions like covalent interactions and all the rest of it. Much of the biology is defined by hydrogen bonds, which play a huge influence. And I think this is an important point which Gautam finished on, is that we need to cross the traditional scientific boundaries, obviously national boundaries, to understand science and go forward. The biology, chemistry, physics, and inorganic, organic, bioinorganic all come together in order to understand a scientific problem. I was particularly pleased to see the list of people who are attending this lecture. They did consist, Gautam, of physicists, chemists, and biologists listening to your talk, and I'm sure they're not disappointed with the breadth and the vision which you described the crystal engineering field. So thank you very much, and it's been a pleasure for me to be here. When I was asked to do it, I had to rearrange my diary for 10 minutes. I was going to be able to only take part in the first 10 minutes, and that would have been unfortunate. And I'm delighted that I was able to be here throughout your lecture. Thanks very much.
Thank you. Thank you.
Iqbal.
Thank you very much, Professor Dr. Samar, and we are really grateful for your presence here today. And with this, I would request His Excellency, Professor Dr. Iqbal Chaudhry, for his concluding remarks.
As Dr. Samar said, this is just absolutely phenomenal. A wholesome experience of listening to someone who has not only developed science, but absolutely phenomenal in terms of the way he presented. Dr. D.C. Raju's presentation was just holistic in nature when he really talks about the history of science and how things come together, where people from different countries have contributed in the development of something which emerged as a very useful tool in various disciplines. And perhaps even more important is that the way he guided us, the way we need to move forward to make science a useful tool for everyone, and then develop values which are beyond religion and national boundaries. And this is exactly what science offers. So I'm extremely grateful to Professor Dr. Gautam Desiraju for his wonderful presentation. He has been a great source of inspiration, and we hope that we'll be able to find some more time of his very busy schedule to have this experience again. And I'm sure that everyone enjoyed, and people have till the last minute. There were about 160 people in among the audience, and I know that there are many groups together also. So we are actually talking about literally hundreds of people benefited from your presentation, Professor Desiraju. Thank you very much, sir. Thank you.
Thank
very
you all
much.
very much once again. Thank you indeed. It's been a great pleasure for me to share some time with all of you.
Thank you very much, sir. And with this, we come to end of our webinar. Again, thank you very much to all our participants who joined us. And a great thank you to Professor Samar and to Professor Gautam for their valuable time today. With this, thank you very much again, and bye-bye, and hope to see you soon in another lecture, inshallah.
Thank you. Thank you.